Welcome to the lecture on global illumination within the course series on computer graphics at KAUST. The indirect illumination has the disadvantage that it is quite costly because we need to evaluate the interaction and transport of light between elements in the scene. It's not just between the light and the scene elements, but every element in the scene, every triangle, every surface patch is potentially transporting or sending or receiving illumination from the scene or towards the scene. We will shortly discuss on this lecture three methods, which we would need to spend maybe entire semester on to discuss them properly. So on this lecture, we will really just sketch the principle of these techniques, and for interested students, you can look up the literature for more details. We will be talking about radiosity as one method, which is a finite element method for light transport. Then we will be talking about a technique called particle tracing. And the third technique which we will discuss is the path tracing technique. Afterwards, we will be discussing the techniques on how to do accurate direct illumination in combination with these indirect illumination methods. So let's recall one of the formulas which we had on the live lecture, where we can see that the surface radiance, Ls, can be calculated as an integral over the entire hemisphere, where we are measuring the incoming field radiance. And the field radiance is coming under a certain angle or from a certain vector incoming k, and we are measuring what is the surface radiance towards the outgoing direction, KO. And then we have the so-called BRDF, the bidirectional reflectance distribution function, which is telling us how much is the light transported from the incoming direction towards the outgoing direction. In this integral, we are also having the value of cosine incoming theta, because you might remember that we had this this opening of our cone, which was then projected on our surface as an ellipsoid, and to correct for the proper area, we used this cosine term. Now, if we simplify the light transport now for the discussion just for perfectly diffuse surfaces with some reflectance value R, then we can take out the BRDF out of the integral and simply perform the integral over the incoming field radiance values. And if we can do this, and we can simplify it as a transport from one surface patch to another surface patch, and evaluating such an integral, we can do as a system of equations, and from this we can compute and solve the light transport problem. Doing it as a finite element approach is called radiosity, and that's its basic idea. So we discretize the surface patches of our scene into n surfaces, and then where we do not know the surface radiance, but as the light transport is within a system of these surface elements, we can solve for the radiance within the system of equations which are of this form, where each surface element is associated with a certain surface radiance, which is calculated from the field radiance, which is a surface radiance of some other surface elements. Here we have again the diffuse reflectance of our particular material, which corresponds to a certain triangle or surface patch, and here we have the term for the emitted radiance from this surface patch. The Kij are just the constants associated with the integral version of this formula. So this is how we conceptually can solve the radiosity as an approach for calculating the indirect illumination. The second method is called particle tracing, and it is based on casting particles from the light source into the scene and depositing the light energy or the light power in the scene. We can calculate the reflectance as a term which is proportional to power per area, and this power can have two components. One is the emitting power of the light, and one is the power of incident power, which is then reflected from given a certain diffuse reflectance. And the reflectance function and the emitting power can be the input variables for each triangle. And with this, we can initialize the first component of the radiance. So for each triangle which has some emitting power, we will initialize its radiance with the first component. And then we will be tracing particles, casting particles into the scene, and wherever the light ray will intersect a certain surface, certain triangle, on that position we will deposit and increase the radiance. And we will increase the radiance of a texel by this incident radiance, which is calculated as the power which has been this triangle been hit by, and normalized by the number of texels which correspond to this area of the triangle. After this has been calculated, we can either send the particle further into the scene or terminate its traversal through the scene based on certain probability. So, as you can see here, we have a light source, and from this light source, we are calculating a certain direction of traversal of the scene, and we are intersecting a certain geometry, and we will be calculating what is the power which is then reflected from this triangle. Now here the diffuse reflectance is for each color component 0.75. For some strange reason, which is physically implausible, we are increasing this power even if this triangle is not really emitting any light itself. And the reason is because the probability of being reflecting is then used for calculating the new power after the after the bounce. Normally, this probability should be higher than the diffuse reflectance values, which is here. But in this particular case, which is in the book, the diffuse reflectance for this triangle is 0.75, and the probability of the bounce is 0.5. That is causing us that we are actually increasing here the power, which should not happen. Normally, the reflection probability should be equal to the diffuse reflectance, and in such a case, we will not be decreasing or increasing the power, but it will be kept constant until we will at some point terminate it, because we will evaluate on each bounce with a certain probability whether we are bouncing further or we are absorbing the light on that particular surface. So we can, if we are outscattering, then, as I said, we will be using this formula for changing the power, and then still at each position of a bounce, we will evaluate whether we are outscattering further or whether we are terminating and absorbing this particle. How do we determine the scattering direction? Well, we are dealing with Lambertian surfaces here, and therefore we should outscatter to the hemisphere with equal probability. So we could use what we have already calculated or obtained from the sampling lecture, where we have discussed that given two canonical random numbers, which are then defining as two random peaks on the interval 0 to 1, and we will transform this fair sampling of the 0-1 interval into the fair sampling of the hemisphere. And you might remember that we are using these canonical random numbers for generating this cosine term and this term here, based on the two spherical angles, which we have, the theta and the phi. And here, in this case, we are multiplying with these components of the coordinates, some basis vectors, u, v, and w, which are calculated on the particular surface. If we have our surface patch, let's say we have a triangle and we have a certain normal, then we define the w as being the unit vector aligned with the normal, and then we are calculating, we are using the u, for example, as a calculation between 2 points, let's say P1 and P2. We calculate the u vector, and then we calculate the v vector as the one which is perpendicular to both of these. So this way we will calculate the coordinate system within, so that we can define our hemisphere. And once we define our hemisphere, we can calculate what will be the random vector A, which is sampled then uniformly over the entire hemisphere, and it's not unfair from the perspective of sampling. Here we have a short pseudocode for the particle tracing, where I have you'll find this pseudocode also in the book. I have added here just this one line on what is the probability of the termination or of the outscattering, and the calculation is as follows. For n particles, compute the uniform random point on the light source, and then compute a random direction B uh, in the hemisphere from this light source or light source geometry, and then we are intersecting a particular element in the scene and at some point C. And there we will be adding this power to this appropriate texel, which is at the corresponding to the point C. And if our canonical random variable is equal to the probability of bouncing off from this surface, then we adjust the power and we define our own surface as its point as the starting point of a ray or of that particle, and then again we sample the B as the random direction in a fairway. And then we are performing this operation until we have obtained the evaluate that we are not hitting any other object or we are absorbing the particle at a particular surface position. So this was a technique, the particle tracing, where we started off from the light source and we were traversing in the scene. And the traversal has resulted into depositing of light energy. And then we had our values of radiance captured in the scene, and then we could just simply render the scene without performing any illumination. The textures themselves will be standing for the illumination, which has been done in the depositing process. The path tracing, on the other hand, follows a different approach. Here, similarly to the ray tracing, we are starting from the eye position and we are following an eye ray into the scene, and we are calculating the illumination at the particular location. However, we do not know what is the incident radiance at a particular position, and therefore we need to calculate it. And the incident radiance we need to calculate by following the second and further bounces until we hit some object in the scene which is emitting light. So this is the principle of path tracing, where we are calculating one path, and at each position we are essentially sampling what will be the next direction along which we want to calculate the incident radiance. So we again have here the light transport equation, where we have the emissive term here. We have again the BRDF, the field radiance, the incident radiance, which we want to calculate in order to obtain our surface radiance. In path tracing, we are using the Monte Carlo integration for estimating an integral of a function. And you might remember that we are doing so by calculating the sum of the values of a certain of this function at particular locations, and we are weighting it by the amount of samples we are performing and weighting it with some probability density function. The probability density function in this case can be, which is here, can be just a cosine density function here if we are modeling and diffuse surfaces. So the BRDF is just a diffusive surface, and therefore with this we will significantly simplify the light transport equation using the Monte Carlo integration strategy and these relatively simple PDF as well as the BRDF. So we end up with calculating the surface radiance as a as the sum of the emitting radiance and the the incident radiance or the field radiance weighted by the diffuse reflectance value. And we perform this on each position, so we need to calculate the incident radiance from the by the next bounds. Path tracing can be realized as a recursive function where in each step of the recursion we will be bouncing one ray in one direction. So we start from the eye, and from the eye, which will be at the beginning at the position A, we will be following a direction of from the eye in the eye vector with which is the vector B in this case, and we will initialize the depth to 0. And then along this this ray, we will intersect a certain surface at the point C. Now, at this point, we will be evaluating the color C. So this is not the same C, I'm sorry. So this is the, let's make this C bold, while the other one will not be bold. And we are evaluating what is the emitting radiance in the direction towards the eye. So in the direction of minus B in this case. And that will be the first contribution of the light. And furthermore, we will be performing the next bounce in order to calculate the incident radiance. So we have our depth, which was initially 0, and then we are increasing this depth in the recursion here, so that we have some limited amount of steps of recursion. And during this bouncing, we do hope that we will be bouncing into the light source so that we can calculate the emitting radiance value and then illuminate by that the surfaces along the bouncing path and eventually towards the eye. So once we are at a certain point C, then we are computing the direction D from there again in a fair way. And then we are calculating the color value from the ray color function as the C, which we have previously computed, and then the recursion, which is then weighted by the diffuse reflectance. So the ray color will continue with the vector C, so I'll make it a bold C, which is the point at the surface, and then into the direction of D, and until we reach the max depth. We hope that before that happens, we have reached the light. Otherwise, we will return the background color. So this is the path tracing, which, as described here, if this realized just for one sample or one ray per pixel, will result in a very, very noisy image. Therefore, we need to cast through our pixel several rays and calculate uh, the radiance for all these rays and sum it up together and average it so that we can have a less noisy image. So the more samples, and often this could be thousands of samples per single pixel, we need to cast in this method in order to have a smooth image. There could be alternative methods based on so-called denoising, where with a smaller amount of samples, we will result into a noisy image, which can be then smoothed in a separate denoising step. With radiosity, particle tracing or path tracing, we can compute the indirect illumination and then sum it up together with a direct illumination, which can be calculated more accurately from the light transport equation. Previously, we have been already calculating the direct illumination in the ray tracing, where we were using the shadow rays for this purpose. The shadow rays we were casting from a surface point and evaluating whether we are hitting the light source or there is an obstacle in between. Generally, for the light transport equation is expressed here as we had it on our light lecture, and where we see that there is again an integral of the all the incoming directions, where we have our incoming radiance. Here we have the visibility term. We have also the distance taken into account, where with the increasing distance, the light energy will be smaller and smaller. And this continuous formulation we can estimate again with Monte Carlo integration. If we just produce one sample from the Monte Carlo integration, meaning that we want to get just one ray illuminating a certain point on a surface, then we can just randomly sample our light source, on its surface, and evaluate its contribution to the particular surface point X. This light transport sampling is having again the probability distribution function, and here this probability distribution function can be computed as the area of the light source and the reciprocal of it. So our Px will be just uniform distribution on the light source, 1 divided by area. So, and in this way, we get the area term into the nominator, and this way we can approximate the light transport. We can see this on the following pseudocode. Here, the direct illumination of a point X with the outgoing direction KO towards the eye and the normal at a particular surface point. So first we pick a random point X prime on the light source, which has the normal N prime, and we do so again with a fair sampling strategy. Then we calculate the vector between these 2 points, and this will be our forming the normalized version thereof, will be forming our incoming direction. And in case there is a direct visibility, so the if statement here is true, then we just calculate what is the emitting radiance towards our direction of the surface point, multiplying it with the PRDF towards the eye. And furthermore, we have the cosine terms in the equation here and here, which we are calculating from the dot product. And then finally, we are having in the denominator the distance squared. Now it is quadrupled because we are normalizing. Keep in mind that the d is not normalized, so therefore the d, in order to normalize it, is coming into the denominator. So this was the calculation how we can obtain the direct illumination component in case our light is a planar geometry. If we have a spherical light source, we have pretty much the same strategy, besides that we need to sample this light source in a slightly different way so that we obtain fair sampling. To make this happen, we first establish a coordinate system UVW, where the W vector will connect our surface point with the center of our light source. Then we calculate the V vector as a cross product between the normal at the surface with the W vector. And then we calculate the U vector of the coordinate system as a cross product between the W and V. And then we are interested in sampling this spherical angle, which is spanned by the alpha max, which is here the maximum angle in both directions. And then we have the second angle, which is the phi, which is the azimuthal angle. And we need to first, therefore, calculate what is the solid angle component of the alpha. And then we calculate the solid angle itself, which we want to then uniformly sample. So the alpha max from this trigonometric setup, based on the knowledge of the diameter or the radius of our light source, can be calculated as the arc sin function of the r divided by the x minus c, which is the from this right angle setup we get the sine of the alpha, and then through the arc sine we get the angle itself. However, the arc sine can be also turned into an arc cos function, because we know that sine squared x equals 1 minus cosine squared x, square root of that. So we just use this knowledge on calculating or formulating the alpha max in a slightly different way. For a solid angle calculation, we can use this formula in order to calculate the solid angle omega, where this is the 2 pi, the phi range of our solid angle, and here we have the component of our alpha, where here we have a cosine of alpha max, and as the alpha max is expressed through the arc cosine, we can just for this term just place in the square root term here. So this way we will have the solid angle, and this solid angle we simply have to uniformly sample. Therefore, our probability density function will be just a reciprocal of our solid angle, which is expressed here. And by following this and the strategies which we had in the sampling lecture by the function inversion, we can obtain again a fair sampling of the spherical luminaire by using the two canonical random variables defined over the interval 0 and 1 for uniform sampling, and we can turn them into fair sampling of alpha and theta, alpha and phi, sorry. So by having these two values, we can then calculate the random sample on the luminaire, which is then realized through fair sampling, and then proceed with the calculation of our direct light component analogously to the planar light source case. So in particular, given our alpha and phi, we can calculate the direction towards the sample of on the light source by multiplying the cosine and sine terms of phi and alpha with our new basis, with our basis vectors. So this will be the value of our vector if we will have just the coordinate system untransformed. So the z will be one direction and the x and y will be the other directions of our world coordinate system. If we have other coordinate system here, we need to simply perform a transformation of this vector in the canonical coordinate system to this UVW coordinate system, as we had on the transformation lecture earlier over the course. So this is how we can calculate the direction towards the light sample. And the final thing which we need to care about is to calculate the probability density function. And previously, our function which we calculated was just the 1 divided by the solid angle, which we now want to sample as the area. So we want to have an areal differential, not the spherical angle differential. Well, we have the correspondence between a spherical angle differential and the areal differential here in this formula, and therefore we can simply change our probability density function for the solid angle qx into the probability density function which is related to the area, and we can simply plug in this back into the equation in order to calculate the sample with our Monte Carlo integration. In case we would like to use non-diffuse luminaries, this means that they will be not reflecting the light in the scene or not casting, not emitting the light in the scene in the uniformly. So each angle is on the hemisphere is the light is emitted with equal probability. We can, for example, have some kind of a Phong-like pattern, meaning that the more the light direction is aligned with the normal of the geometry of the light, the higher the probability. So, for example, here we have the normal vector and prime of the light, and we can perform some cosine term weighting of our probability or of our to calculate our emitting gradients. If we furthermore, on the light source, want to have a non-constant light, meaning that we want to have a certain pattern on our light source, like for example on a TV set where we will have a particular pattern on the TV which is at the same time serving as the light source, then the the excitant radiance term here will also not be constant along the light source. So here one aspect is the direction of the light source. If we are sampling from a direction which is not very much aligned with the normal vector of the light source, then the excitant or the emitting radiance will be downscaled, will be smaller. And then we can also have the excitant radiance term, which will be a function over the light source surface instead of being constant. With this, we have covered all the basic techniques of indirect illumination, such as radiosity, particle tracing, and path tracing on the conceptual level. And we had discussed how to perform an accurate direct lighting of the scene, as we would like to have a direct light component and the indirect light component calculated separately, and then for the final results to be summed up together. That's all for today. Thank you for your attention and see you at the next lecture.